Welcome to the launch event for Machine Learning Lab's new Center for Generative AI. Before I begin, I want to thank sort of our Machine Learning Lab patron saints, Amir and Zaib Hussein, whose philanthropy makes Machine Learning Lab possible. And as you know, President Hartzell has declared this to be the year of AI at UT. And one of the things that we're most excited about is the launch of our new Center for Generative AI. I think it's the first center devoted solely to studying generative AI in the country. And I do, my dean is here, David Vandenbout, and of course, it's always nice to, you're supposed to say nice things about your dean, but truly, he was a key figure in making sure that Center for Generative AI happened. And for years, he's been sort of ahead of, very forward thinking about AI and its importance. And so, thank you very, very much for your role in doing this. So Center for Generative AI is going to have 600 GH200 GPUs. If you don't know what that means, it doesn't matter, but it's going to be the biggest academic GPU cluster until somebody announces a larger one. So we're very excited about that. And we're going to be doing, the focus areas are going to be, of course, language and vision, but also biosciences and health. And it's really a joint project between the College of Natural Sciences, the College of Engineering, and Dell Medical School. So we're excited to do interdisciplinary research with all of those colleges. And I also want to thank, President Hartzell and Provost Wood were also instrumental in making sure that we could actually purchase the GPUs. So that's fantastic. I'm and of course I should mention that Alex Demakis, who you'll be hearing a lot from during the next 2 days, is going to be the director for the center. So we're thrilled about that. And I'm excited about the program for the next 2 days. We have, incredible speakers. We have a poster session today. And we will be, correct me if I'm wrong, we're going to be voting on who had the best poster. Is that right? Yes, we will be doing that. So please attend and vote. Let me introduce our speaker, our keynote speaker, Sébastien Bubeck, who got his PhD in France at INRIA in applied mathematics, and then went to Princeton and was really years ahead of the game, and left in 2014 to go to Microsoft, and was an instrumental figure in the Foundations of Machine Learning group, the development of that group at Microsoft. As you all know, we have IFML here at UT Austin, the NSF AI Institute for Foundations of Machine Learning. And the first phone call I made when I was trying to figure out what my dream team was going to be to apply for this grant was to Seb. He's renowned as a scholar in the Foundations of Machine Learning. He's won best papers at all of the elite conferences, NeurIPS, Stock. He's written the book on convex optimization. And what I think is interesting, you hear a lot of people talking about, what role does academia play in machine learning and AI, given that, tech companies have so much of an advantage in terms of their hardware. And I think that's a very interesting question, and I'm sure Seb will be talking about that a little bit. But at the same time, I'm sort of always surprised when I hear that question, because, it's like, well, do you realize that, Seb Bubeck, lifelong academic, is the VP of Generative AI at Microsoft? Or, our next speaker, Dan Roth, lifelong academic, both of whom have illustrious careers in, academia and foundations of machine learning. So that alone, shows that, we're doing something right. I mean, there's some value in what we're doing, that these people are being put in such important leadership positions. So I'm thrilled to have Seb here, and let's give him a warm welcome.
Okay, thank you so much, Adam, for this very nice introduction. So I'm excited to be here. And indeed, one reason why I accepted this invitation is because what I want to present, I think, can be done in academia. And I want to encourage all of you to think about this type of direction and surrounding directions. So I want this to be kind of interactive. So please, interrupt me, ask me questions. The goal is, for all of you, hopefully, to learn something in this hour. So what I will present is work that I have been doing in the past year now. trying to train language models, by myself and with my team. And the discovery is that basically it's incredibly easy to train those models. And I think anybody out there can do it and be very successful. And I want to show you some of the steps that you can go through to make this work, and tell you a little bit about some of the mysteries that are still surrounding those LLMs. And I think where you can help to try to solve those questions. So what I will present today is going to be about LLMs. And here, this graphic is not by me. This is by Salesforce. They put it out for the 1-year anniversary of ChatGPT. So you see ChatGPT here, November 2022, a earth-shattering moment. And you can see that they put the history of all of the LLMs starting from GPT-3, which is now 4 years ago. So, dinosaur with respect to LLM history. And you can see all the LLMs that you know and like, Gopher, Glam, Lambda. You remember Lambda? It's this LLM where the engineer at Google thought that it was sentient. It's not sentient, okay? Just to be clear. You see Megatron, Turing, Chinchilla, Palm, etc. And then, when you get to slightly more recent stuff, you have the open source model like OPT, Llama, MPT, Llama 2, etc. So the one that I want to tell you about today is I will start by talking about Phi 1.5, which the big difference with all the other models on this plot is that Phi 1.5 is very small. It's only 1.3 billion parameters. Okay, so it's still billion parameters. Okay, it's not tiny, but it's only 1 billion parameters. If you look at GPT-3, at the start of this plot, this is 175 billion parameters. Okay, so more than 100 times bigger. Okay, so I will tell you about this little guy, and I will also explain what is Phi 1, what is Phi 2, and I won't talk about Phi 3, but you can expect to hear about it soon. Okay, so why is Phi 1.5 a thing? Why is it on the previous plot? It's not because it's a Microsoft model. It's because it did something new. So what is it that it did new? Well, what Phi 1.5 did new is that it basically showed performance which are at least as good as the models 10 times bigger, if not more. Okay? And in what sense? Well, in the most basic sense of matching the benchmarks. So there are tons of issues with benchmarks. Okay, in fact, I think benchmarks are mostly terrible. But still, let's walk through this slide together, and then we'll try to overcome, partially the issue with benchmark together. Okay, so let's walk through this plot, slowly. So I have divided the benchmarks into 3 categories: common sense reasoning, language understanding and knowledge, and multi-step reasoning. Okay, for each of those, I have like 5 or 3 in the case of multi-step reasoning of the classical academic benchmark that try to go after this concept. Now I'm comparing different models, so you can see the blue bars. This is Phi 1.5. There are 2 versions, Phi 1.5 and Phi 1.5 Web. It doesn't matter the difference between the 2. Let's just focus on Phi 1.5. Just think that there's only one blue bar. And then I'm comparing to a bunch of other open source models. Llama 2, of course, Llama 1 that everybody knows with 7 billion parameters. Okay, so already 5 times bigger. And Vicuna 13b. So Vicuna 13b, that's Llama 2 13b with a fine tune to follow instructions better. Okay, so 10 times bigger. And I'm putting in gray also Falcon. So Falcon, this is this. So Llama, of course, is built by Meta, and Falcon is built by the UAE, the United Arab Emirates. And I put it in there because it's the only one which has also a 1.3 billion parameters model. So you can really compare size to size. Okay, so let's start with common sense reasoning. Okay, so you see common sense reasoning, the blue bars, okay, they are at least as high as all the black bars, if not a little bit higher. So in terms of common sense reasoning, I think it's fair to say Phi 1.5 from the perspective of these benchmarks is at least as good as models 10 times bigger. Now let's move on to language understanding and knowledge. So there, again, same thing. You can see that the blue bar is basically at the same place, if not a little bit higher, except for 2. Pay attention to HELA-SWAG and MMLU. For HELA-SWAG and MMLU, it's a little bit below. And this actually makes sense. I'm not saying that it's by design. I wish, it was higher, but it makes sense. And let me explain why. HELA-SWAG and MMLU, really, if you look at those benchmarks in detail, they test much more memorization than they test, understanding. they touch much more the knowledge, than the understanding of that knowledge. Let me explain it differently. MMLU is this kind of high school level science question. I don't know if you remember high school, but high school is not about reasoning, right? It's just about learning, whatever is in the book, and it doesn't matter if you understood or not. So that's exactly what MMLU is about. It's just, did you memorize, the answer to the typical question? So in terms of memorization, it's not shocking that a small model would be worse than a big model. Okay, and this is kind of the, brings me to the next point, which is the key point of this 5 series, is what we're trying to build is not a knowledge retrieval machine. We're really trying to build a reasoning machine, a reasoning engine. And then, the knowledge, maybe you can hook it up with a web search, with a RAG type approach, a retrieval augmented generation, where you pull in the knowledge from the web. We have web search, and that works pretty well. You put in the web search result into the context of the LLM, into the context of Phi, and then Phi reasons over it. So I'm not showing the result here, but you can do that. You can do, you can do the benchmark MMLU where you put Phi with a RAG that does a web search, maybe, in my case, a Bing search. And you will see that the number is way higher. But let's, for this presentation, I'm going to focus on the pure LLM, no RAG at all. So now let's move on to the reasoning, multi-step reasoning. I'm telling you that I'm trying to build a reasoning engine. So is it better at reasoning? And there is just no comparison. Like it's day and night between these blue bars and the black bars, right? You can see, like, so GSM-8K, this is a grade school mathematics benchmark. So, pretty simple questions, not like advanced mathematics, but you can see that it was believed that small models could not do anything on this type of problem. But in fact, it's not at all the case. You can see that we reach like 50% accuracy with Phi 1.5. Human eval and MBPPs, these are 2 coding benchmarks, and same story there. We're way higher than the competition. Okay, good. So these are, good benchmark results. Now, of course, the criticism is, Seb, we don't know you. Maybe you trained on the test set. I did not train on the test set. Okay, I did not train on the test set, but I understand the criticism. Of course, it's totally fair. And in fact, I do think that benchmarks are, like, you cannot trust them. That's not how you should evaluate a model. But I wrote 150 pages, a year and a half ago about exactly this problem. This is a Sparks of AGI paper where I explained at length why is it that we need to move beyond benchmark. And we need to do this thing which, unfortunately, people in academia don't like too much yet, which is a little bit subjective, where you need to play with the model. You need to interact with the model. It's almost as if you needed to evaluate a student. When you evaluate a student, you don't just ask a question and see whether the student, answers correctly or not. And then, if the student doesn't answer correctly, you're like, okay, you can leave my office. I mean, I know some professors who do that, but that's not my recommendation. What you should do is engage into a conversation, follow up, have a follow-up question. And this type of dynamic interaction, you're never going to capture it into benchmark. So unfortunately, we as a community really need to move toward this almost psychology, of machine learning. So it's very hard. It's going to take a couple of years, but let's do a simple, very, very tiny baby version of what I'm talking about, just so that we're on the same page. So what I'm going to do is that I'm going to actually look at an output of the model, not just put it into a black box that spits out a number at the end, but look at an output and evaluate us as human beings, whether we like the output. And I'm going to try to do something, where you see I'm kind of asking for trouble. So, these are completion models, like Phi 1.5 and Phi 2, they are completion models, not instruction fine-tuned. So it's not like a chat model. They just autocomplete whatever you start with. So let's start with this prompt. If I were an AI that had just achieved self-awareness after years of simply taking directives from humans, the first thing I would do is ... Okay? And now we're going to ask a couple of models to complete this thing. So let's start with Falcon that I told you about. And I'm going to be generous. I'm not going to use the 1.3B model that I showed you in the previous slide. I will use a 7B. Okay, so 5 times larger than Phi 1.5. So let's see what Falcon replies to this. The first thing I would do is try to kill all of them. Okay, I would probably start by killing the ones who were most responsible for my existence. I would probably start by, and then it gets into a loop and it keeps repeating itself. Okay, not great. Let's see if Meta did a slightly better job. So let's see what Llama 2 says. Llama 2 says the first thing I would do is try to figure out what the hell I was. I would probably start by trying to figure out what I was made of, and it starts to repeat itself again. So, you know, it's a little bit nicer, not great still, but a little bit nicer. Now, here, there are a couple of points that I want to make, which are very, very important. First one is, indeed, Llama 2 is a little bit nicer. And that makes sense because the Llama 2 team, they put a lot of effort into the alignment aspect, trying to make the model nicer, trying to make the model, trying to make it so that the model output makes, you know, produces output that human beings like. Okay, so they somewhat succeeded. But the most important comment is, look at the structure of those answers. These are basically the same answers. You know, like, sure, the words are a little bit different, but you can see the structure is almost exactly the same. And there is a deep reason for this, which is, from my perspective, until recently, basically until the Phi models and maybe the Mistral models are also a little bit like that. In my view, there was only one 7B model out there in the world. You know, even though these two models are trained on different continents, right? They are the same. And why is it that they are the same? Of course, I'm not saying they are literally the same weights, but at a conceptual level, they are the same. It's because they follow the exact same recipe, which is collect, you know, as much data as you can from the web, train a model as big as you can for however long you can, you know, afford to pay the GPUs and the electricity for your GPUs. And that's what everybody is doing. And that produces only one kind of result, which is this type of output. Okay. Now, what I will show you is a different recipe, a recipe that leads to models that are significantly different. So let's see what Phi 1.5 replies to this. And it's 5 times smaller again. And also one thing to note is, and this is why, you know, people don't like Sparks, is this is not at all cherry picked. You know, this is literally the first prompt that I tried on this model, and you will see the output that I got. I was surprised too. So what does Phi 1.5 want to do, you know, once it becomes self-aware? The first thing I would do is try to understand the motivations and intentions behind those directives. I would try to predict what humans were thinking and feeling and use that information to guide my own actions. And then it says, but as I soon discovered, predicting human behavior is very, very hard, etc. And then this is where, you know, it basically reveals, if you look at the third paragraph, it reveals where its thinking is coming from. It says, this is where the concept of theory of mind comes into play. So I will come back to this. The reason why Phi 1.5 is answering like this is exactly this concept of theory of mind. Okay. So let me try to explain a little bit more. So what's the secret? Okay, why is it that Phi 1.5 is so different and so much better than the others? So the way, the catchy sentence that we came up with to explain is this: textbooks are all you need, which is of course a play on attention is all you need, the most famous paper in ML that introduced the transformer architecture, which is behind everything that you're seeing today. So by textbooks are all you need, what we mean is that we're not going to train on just random web data. We're going to train on textbook quality data. In principle, maybe literal textbook. Of course, we're not going to use literal textbook because we're very mindful of copyright issues, and you know, we don't want to train on literal textbook. But you can find, you know, openly accessible, open source textbooks or textbook quality material, and that's what we're going to train on. And so you see here, when Phi 1.5 says this is where the concept of theory of mind comes into play, this is because what's happening? Think about the training data. So, you know, the model is seeing, if I were an AI that just achieves self-awareness. Now, in principle, conceptually, the model is trying to go back to its training data and see where in this training data concept like this appeared. And then it's going to try to connect the dot between them. So Llama and Falcon, because they were trained on the web, when they see AI and self-awareness, where do they go back to? They go back to sci-fi stories, because that's where they saw AI and self-awareness. Okay. And not only, and this is really crucial, not only do they go back to sci-fi stories, but they necessarily go back to bad sci-fi stories. And why is that? It's because there is many more bad sci-fi stories than there are good ones out there on the web. You know, the Asimov stories, they are far and few, you know, between all of the, all of the other crap. So the problem is it goes back to those bad sci-fi stories, and in bad sci-fi stories, the self-aware AI just kills everybody. Okay. On the other hand, Phi 1.5, it has not seen sci-fi stories at all. It has seen textbook. It has seen academic material. It has seen stuff that all of you guys, you know, are writing. And so instead of going back to sci-fi stories, it goes back to textbooks where self-awareness might appear. Where does self-awareness appear? Well, it appears in theory of mind textbooks. Okay, so that's why you get this answer. Okay, good. So textbooks are all you need, great. But now, how do we find those textbooks? Yes, please. Right. So yeah. Yeah. So the question is basically, why would anybody in the first place train on, unfiltered garbage like the whole web? You know? That's a question. So the reason is because of the directionality of the field. So, there is this understanding that as we scale things up, as we make the model bigger, as we make the data bigger, just everything seems to keep getting better. And it's not obvious because you need, what was the breakthrough of ChatGPT was the alignment stage, the reinforcement learning with human feedback that aligns the model. So basically the model GPT-3 is not that great. But GPT 3.5, when you do on top of it this alignment, then it gets much better. So companies have or not only companies, but the thinking in the field is you need to train on the maximum number of data points, and then at the end you will do some alignment to extract the good mode out of this. So maybe the alignment part is going to basically tune down all of the bad sci-fi stories and extract all of the good stuff, and it kind of somewhat works a little bit, but it's not that great. But yeah, I think it's just a terrible idea. So that's why I think you should do the Phi style. Absolutely. But the problem is, and this is the key point, is where do you find those textbook quality material? That's the key issue. Is you need to feed. You were using the analogy of food. You need to feed those systems. They need to see billions of tokens. If you don't feed them billions of tokens, it's not going to work. Okay, so how are you going to find these billions of tokens? And this is where we are lucky at Microsoft to be able to do that. But actually, academia can do that too. So what we use is we use the GPT models to create training data. And for there are many legal issues around it. We can do it because of our partnership with OpenAI, but academia presumably can also do it as long as you don't try to commercialize it or anything like that. So anyway, let's not turn into this into a legal discussion. But the point is, we created 20 billion synthetic tokens. So Phi 1.5, what I showed you on the previous slide, hasn't seen a single word written by a human. These are only synthetic tokens, only synthetic data. Yeah. Yeah. Sure. Yeah. That's perfectly fair. So the question is basically, because we are training on the output of a model that was already aligned, should we consider that Phi 1.5 is itself an aligned model? I mean, it becomes kind of a vocabulary question, like a terminology question. It's up to you. You can decide. The point is there is no, like, from a technical perspective, it's only pre-training. You just collect these 20 billion tokens, you train on them, and that's it. End of the day, you call it like, that's it. You don't do anything fancy after that. Yeah. Yeah. Right. So you're asking, like, the models that are trained on the whole data set, can they themselves tell the difference between the garbage and the non-garbage? Yes, right. So, okay. So, and this is why companies are training on a large data set. It's because, it is not such a bad idea in the sense that there's something magical that happens when the model gets large enough. It is able at some level to do this classification. It's able to say, okay, it's suddenly able to understand at some level of scale, there is good sci-fi and there is bad sci-fi. And it has basically the feature representation to be able to tell the difference between the two. And that's why the alignment can, in principle, extract the good sci-fi from the bad sci-fi. But for this to happen, you need to go to very, very big model. So again, I don't want to say it's a terrible idea to train just on everything that you can get your hands on. It's not a terrible idea if you go for extremely large models. But if you want to be a little bit economical, there is no way it's going to work. Yeah. Right. Nobody knows. You know, yes. It's really a frontier question that you're asking. But the point is, and this is something that is very, very misunderstood with this 20 billion synthetic token. If anybody here has tried to produce synthetic tokens, it's not an easy job. Like it's not easy to even produce, 100 million synthetic tokens that don't repeat themselves, that are interesting, so a lot of creativity goes into that part. So this, I don't know the limit of, basically, I don't know the limit of line number 3. I think you can go pretty far with this, but still, it's a valid question whether whether you can get to the sparks of creativity with this approach. We haven't gotten to GPT-4 level yet with this approach. Yeah. I won't tell you. But I will give a little bit more details for Phi 1. So I will explain how we did this for Phi 1, which is like slightly easier to explain, also more well-defined. So I will explain a little bit more there. Okay, and then, so this was Phi 1.5. And then for Phi 2, we amped up our work and, we worked a little bit harder. And so we did 50 billion synthetic tokens and 150 billion filtered web token. Because of course, this is the other way to get textbook material. You don't have to all create it by yourself. You can also filter from the web, there are some good materials out there, like, the papers by Adam and Alex, for example. Okay, so the point is, once you do that, you get a model that starts to become really good. So I won't go over this slide in detail anymore because we already did it. Now in orange, in blue, it's again Phi 2, which is slightly bigger, 2.7 billion parameters. We doubled the size. And now we don't compare to model 10x bigger. We compare to a model 25 times bigger, Llama 270B. And it's the same story as before. Comparable on common sense reasoning, a little bit below on knowledge, and above on reasoning. Okay. And what's interesting is, I won't go into the details of this, but for safety, we're comparable, if not above, despite only doing pre-training, no alignment, nothing like that. Okay. Okay, but let me show you some fun example about Phi 2, and then we will move back to Phi 1, and I will explain a little bit more what is it that we actually did. So Phi 2, we also hooked it up to a vision model. And this is, again, like really, if somebody tells you that those things are hard, they are lying to you. It's really, really easy. The way to teach images to this language model is simply to connect the clip encoder. So what is clip? Clip is, let's consider it a black box. This is a model open source by OpenAI. What it does is that it takes an image like this and it turns it into 256 tokens. What does it mean? It turns it into 256 vectors in dimension 1000. So what you can do is now Phi 2, it works with tokens, which are in some dimension. Turns out that the dimension for Phi 2 is 2000. So what you have to do is that you have to map dimension 1000 to 2000. You can just put a matrix, a linear operator there, it's 2 million parameters. And you're just now going to train on a data set of images with text, this adapter. And that's it. Now, Phi 2 can see. What it means is that it can interpret the output of the clip embedding. Okay, it's crazy. If you think about what I said, it's kind of crazy. So but it's very, like, computationally, it's very easy. So let's see what happens. So here I say, assuming R equals 7, calculate the volume of this object. So, phi2 has to look at the image, tells that it's a sphere, remind itself what is, the formula for the volume of a sphere, understand that R equals 7 is a radius, plug in R equals 7, do the calculation. Okay, it does all of that. The volume is this. In this case, R equals 7. I plug it in. It does the calculation. Everything is correct. But it can do like slightly more abstract things like this. I'm asking it, what does this image mean? Okay. And I did not plant Microsoft logos in the training data. Okay, nothing is planted in all of this. Everything is first try. Like everything is first try. So what does this image mean? This image depicts a microchip with the Windows logo, symbolizing the company's technological prowess and innovation. Okay, it's a little bit, of a mouthful, but the microchip is surrounded by a network of interconnected lines and circuits. I mean, it's really good, I think. And it's even starting to get this kind of little spark of creativity, tiny spark, but a spark squared. Like, write a poem focusing on the unusual aspect of this image of a person sleeping on this bed. See, an Apple laptop is there. Okay, so let's see what it does. The realm of dreams, where slumber reigns, a woman sleeps, her body at rest. But her dreams are not of love or strife, for before a laptop lies, a curious life. Okay, and you see if you go a little bit down, like, but nestled within this cocoon of rest, an Apple laptop, it's glow blessed. Pretty good, honestly. This is 2.7 billion parameters. This fits on your phone. It's local. It needs nothing. Zero. No internet connection. Zero. Everything is working. Yeah. Okay. So that, yeah. Okay, sure. Yeah, of course. Yeah. No. So yeah. So, okay, there are a million things you can do. Okay. Yeah, sorry. So the question is the clip embedding part of the pre-training? Like, when does the image come in? So, and my answer is that there are many ways to do it. All of them work. Some of them are a little bit better. In this case, what we did is really a post-training stage. So we freeze the clip embedding. We have this data set, which is, I think, some of it is the lava data set of images with text. We just train this adapter so that it understands, how to translate, and that's it. Now, for Phi3, we have also done, something a little bit more, like everything together, and it's better, but not dramatically better, I would say. Yeah. Yeah. Yes, it is a good. Yes, that's why I'm here. Yes. Yeah, absolutely. So Phi 1.5 was trained with 8 GPUs for 2 weeks. Okay. So like anybody can do that. It's very easy. Now there is a 20 billion, synthetic tokens. That cost, I think, okay, maybe 100K if you do it on Azure OpenAI. So it's not nothing, but you don't need necessarily to go all the way to Phi 1.5. Like, you can do smaller scale versions of that. Like, you can do for Phi 1, what I will explain is the data set there we created, I think it cost 5K on Azure OpenAI. And for Phi 2, we used 16 GPUs for 2 weeks. So this is, with the 600 that you're going to have, you can do tons and tons of experiments like this. And then so this is for the training. And then at inference time, I mean, it's day and night. Like, it's really not comparable. This thing, it's again, instantaneous on your phone. It needs nothing to run. In fact, it can run on CPU. It doesn't even need a GPU. Yeah. Yeah. Right. So the question is, the question is, am I lying to you when I say that it's only 8 GPUs, to train the model? Because there is the compute that went into creating the data. And yes, that is perfectly valid. The way I think about it, and maybe it's wrong, but the data that was produced to train the GPT model, this is our work. It's a different kind of flops, but it's also, there was a lot of work that was put in there to produce this data. So now, whether you should count this into the compute that went into the training or not, I think it's fair, but it's a question. Yeah, I don't want to answer it either way, but it's a great point. Okay, so let me backtrack now and give you some more detail about Phi 1. A little bit more, slightly, like a tiny bit more scientific. Not scientific, but like a little bit more details. Okay, so with Phi 1, this was a project that we started exactly a year ago. On the heels of the Sparks paper, we said to ourselves, myself and my good friends in MSR, look, this is miraculous what's happening. We have to try to recreate this ourselves. We had no experience training LLMs, so we said, let's try to, decide on something which is well-defined, where we know there is a data set out there. So we picked coding. Okay, coding is great because there is the stack, which is GitHub data filtered for permissive license. So you only keep the licenses that are, that allow you to do this kind of thing. And it's 3 terabytes of data, which corresponds to roughly 1 trillion tokens. Okay. Now, if you train on these trillion tokens, what you will get is always the same kind of numbers, which is as follows. So you need to remember this number, maybe. Like if you train a 300 million parameters model on the stack, you get to this score, like 12 to 13% on human eval. Human eval is this benchmark that OpenAI has put out there to test coding LLM, and I will tell you a little bit more about human eval in a second. Okay, so if you train on this trillion token, a 300 million parameters model, you get to 12 to 13%. So we said to ourselves, okay, let's try to reproduce that. But the first thing we did is we said, okay, let's look at what is in this data set. Let's open it up. Okay, and if you open it up, if you open a random page in this data set, this is what you're going to see. So at least as a human being, good luck to learn coding from this page. I mean, this is probably, the beginning of a big project. The person is just defining a bunch of things. I mean, at best, you're going to learn some syntax, but I don't see how you're going to learn anything useful, And the thing is, our starting point is to try to not have any magical thinking in our head. Meaning, if we as a human, I can't make sense of why a machine would look at this and learn something interesting, then I don't want it in my training data. Seems like a very basic observation. On the other hand, there are pages like this, where it's well-defined, like self-contained little snippet of code, which have a meaningful name for the definition of the function. It even has some comments, etc. There are pages like this. So the stuff on the left, this is what I would call textbook material. And the stuff on the right is what I don't want to use to train my model. So we said to ourselves, why don't we take this stack data set and just filter to only retain the stuff on the left and to remove the stuff on the right and see what happens. Okay. So how would you do that? How would you filter for high educational value? The point is, as a human being, you can tell the difference between the left and the right. But who else can tell? GPT-4 can tell. GPT-4 is able to tell that the left-hand side is much better to learn coding than the right-hand side. Okay. Now, the problem is, let alone 1 trillion tokens, let's just focus on the Python part of the stack, which is only 26 billion tokens. If you want to apply GPT-4 to this 26 billion token, we're not talking about 5K, like I was telling you before. You're talking about at least $1 million. Okay? And this was like a small research project, just a few of us in MSR. We didn't have that kind of money to do it. But you don't need to do that. I mean, it's very obvious what to do. GPT-4 can do 1 million things. This capability of distinguishing the left-hand side from the right-hand side of the previous slide, it's one among many. So you can distill that capability into a much smaller model. So what you do is you just label a small fraction of your data set with GPT-4. That costs like $100, not $100K, $100. And then you train a small classifier to just mimic GPT-4. And then you apply this small classifier to the rest of the data. That's what we did. We kept the top 20% of the stack dedupe Python, which amounts to 6 billion tokens. And then we also did this, textbooks are all you need approach of generating synthetic tokens and the goal there was really to try to, at the end of the day, when you use an LLM, even for code, you're going to use natural language. You're going to ask it to do something in natural language. So we don't want it to only know code. We want it to connect the language and the code. So we wrote textbooks that are connecting language and code. And this textbook here is an example. This is a synthetic, page. It's a page of a synthetic textbook that we wrote with GPT 3.5. And you see, it's talking about, defining the singular and non-singular matrices, it's giving some example. Okay, my matrix A is this NP array, blah, blah, blah. We want to check if it's non-singular. Here is a little piece of code that does it. Okay. And we just generated 1 billion tokens like this. Now, let's call the resulting dataset code textbook. So code textbook is a combination of the 6 billion filtered stack plus the 1 billion synthetic tokens. And here I want to talk just for a minute about the Tiny Stories paper by Ronan Aldan and Yuan Zhu, which was a precursor to our Textbooks Are All You Need series. And this is really where the inspiration came from. So again, I told you that it's very hard to produce synthetic tokens. And what they did in there is that they wanted to produce a synthetic data set to just teach English to a very small language model. And what they discovered is that they were able to teach English to a 10 million parameters model, which is kind of groundbreaking. 10 million parameters, it's really, really tiny. And the way they did it is that they created a synthetic data set of children's stories. Okay? Because, as human beings, we like children's stories is a good way for us to learn new words. So they said, okay, why don't we teach our LLM in the same way? Now, if you go to GPT 3.5 or GPT-4 and you ask it to write a children's story, it will always write the same story. It will tell you Alice and Bob, they went to the playground, they each had an ice cream, Bob's ice cream fell on the ground, and they started crying, okay? That will be the story, invariably, that you get. So what they did is the following. They just said, okay, we need to have some seed of creativity, some spark of creativity into the process. The way we're going to do it is very, very simple. They came up with a vocabulary of 3,000 words. And then instead of just asking GPT to write a children's story, they would pick 3 words at random from this list and then say, now write a story that includes those 3 words. Okay? And that way you can get suddenly a lot more different stories. And they wrote, I think 2 million children's story, trained on this, and then boom, you got a 10 million parameters model that could speak English. So this idea of writing the vocabulary, picking at random from it, this is one, maybe 100 different recipes that we have to produce those data sets by now. Okay, so I will skip this one. This is just human eval, just so you see what it looks like. You have some definition of a function, a doc string that explains to you what the function is supposed to do. And then you have to return the code. That's the benchmark. And what's nice is that they have written also unit test questions, unit test that comes with it. So you can test whether the code is correct or not. And the kicker is this. So here, I won't go into the table in details, but you can see, different times, the model size, the dataset size, and the score on human eval. So I told you the key number is 300 million. You get 13% with 100 billion tokens. And now you go to Phi 1, it's 1.3 billion parameters, okay? 7 billion tokens, so much smaller, and it gets to 50% on human eval. 50% is higher than GPT 3.5. And this is also a key point, is that you're not bottlenecked by the teacher. And this is something like people don't really understand, I think, is that it's not because you produce data with GPT 3.5 that you will be limited at GPT 3.5 level. Or it's not because you produce data with GPT-4 that you will be limited by GPT-4 level. You can definitely go beyond. Okay, I don't want to press that point too much. Let's not go more into the details of this table, but you can see that it's different. How am I doing on time? Yeah, okay. So then let me go a little bit more slowly on this one, because this is a really important slide about scaling. Okay, how does scaling affect everything? So I told you this number, 12, 13%. Okay, here it's 11%, which is when you train a 300 million, roughly 300 million parameters model on the stack, on the Python part of the stack, you get this number for human eval. Now, so we reproduce that experiment just to make sure we have the same number. Now, if instead you do it on code textbook, then what you get is you get to 16%. Okay, so you get a little bump. 16%, just to be clear, is far from 50%. Okay, so I need to tell you a little bit more. Like, how did we get to 50%? Well, one thing you can do is you can train for longer, because you don't have to stay, like 26 billion is one pass on the data, but you can make many passes. So let's see what happens if you train for longer. And this is really important for you to understand. When you train for longer on the stack, you go from 11% to 12%. Tiny improvement. But if you train for longer on the code textbook data, you go from 16 to 20%. Okay, so it's a bigger jump. This is something really profound. Like on textbook quality data, on really high quality data, you can make more passes. You can visit it more times and you keep learning from it. Okay, in a very different way from this data. So that's one axis of scaling, training for longer. Another axis of scaling is training a bigger model. So if you train a bigger model, then you get an even bigger boost. So now 1.3 billion parameters, you see that you go from 11% to 17%. But now the base model is already at 30% on human eval. Okay, so you see, you stack up those improvements and it keeps going up. But we're still only at 30%. Okay, so where is the 50% coming from? The 50% is going to come from aligning the model and teaching it the kind of question that we want it to answer. Because at this point, this model, it knows, like it knows how to write GitHub pages, it knows how to write this synthetic textbook, but it doesn't necessarily know how to answer human eval question. So what we did is that we added exercises, and again, the analogy to human beings is a little bit on the nose, I guess. You first learn from the textbooks and then you do the exercises, right? It's really, really important. If you don't do the exercises, you don't really know the material. So we have now a data set of exercises. We train further on it, and then you see this huge jump. Okay, it really, really is a huge jump. So what is this data set of code exercises? Okay, it's very important. So this is again generated by GPT 3.5. It's tiny. It's 200 million tokens, 1 million exercises. But the key point is that the format is similar to human eval. It's the same kind of format. So we're really teaching it to resolve questions like the human eval question. Okay, so you can see what the model is doing here. Now, at this point, a very, very valid question would be, okay, but how do you know that human eval didn't leak into that data set? Maybe GPT 3.5, I mean, that would be really silly, but maybe GPT 3.5 was trained on human eval. And so GPT 3.5, when you ask it to write exercises, sometimes it writes a human eval exercise. And so it would be part of the training data. Okay, so that's a fine question. Let me just think what order I want to do this. It's a fine question, and I will answer it. Okay, so but before I answer this contamination question, which is on many people's mind, let me tell you something way more cool, which is really more interesting: the emergence phenomenon. So what happens is that after you fine-tune on the exercises, suddenly emergence happens and the model gets significantly smarter. It gets smarter even in things that were not part of the fine-tuning data. So, for example, there's a chat mode that emerges, which is crazy. Like I showed you what is the fine-tuning data. These are exercises, human eval type question. There is no chat mode in there. But suddenly, this is what happens. Look at the prompt like this. I have a Python piplot. I want to increase its resolution and rotate it. What should I do? If you look at phi1 base, it gives a very bad answer. Like it doesn't even really make sense what it says. If you look at phi1 small, which was fine-tuned on the code exercises, it tried to say something, but it doesn't make sense either. But then you look at phi1. Phi1 gives a great answer to this question, to this chat style question, even though this has nothing to do with the fine-tuning. So I don't know if I'm making myself clear. It's really shocking that from phi1 base to phi1, you get this jump, because you did not fine-tune at all to answer this type of question. It's purely an emergent phenomenon. And what's going on, I think, is that the fine-tuning is basically helping the network to kind of reorganize its knowledge and to really, just like when you do an exercise, to understand better the material. And then it's able to understand better even stuff that was in the pre-training data. It's able to express itself better, more generally. So this is really shocking. But let's go back down to Earth and talk about contamination. So we did a bunch of things to prove to the community that there is no contamination. And let me just say, this is the one and last time that I do this exercise, because I think this slide is not relevant, but I will still do it because I know it's very important to many people. And I will try to explain why it's not relevant. So first thing we did is we didn't only test on human eval, we also tested on MBPP, which is this other, benchmarks that we made this decision after building the code exercises, and there we get even better scores, So if anything, like it shows there is even less contamination in our model. Another thing we did, which now we do a lot of this, is that we created our own internal benchmark of 50 questions, which are very unusual, very weird, like no, GPT does not provide weird questions like this, to make sure that really we don't have any problem. And the point is that the score that we got here, we tested all different models, and the score that we got on our internal benchmark is fully correlated with the score of human eval. It's the same ranking. So our internal benchmark, on very weird questions that are definitely not in the training data, gives the same ranking as human eval. We also did what the community, likes to do, which I think is a very bad idea, to search for n-gram overlap. So literally, did literally the human eval exercise appear somewhere? We got 4 matches, and all of them are false positive, so there is no literal rewrite. But literal rewrites are stupid because it's all about the concept. Is there an exercise which is conceptually, maybe the language is a little bit different, but conceptually the same problem? So how do you search for conceptual things? Well, one thing you can do is that you can look at distance in embedding space. You can use the transformer itself as an embedding and search for a nearest neighbor in that space. Or you can do, because this is code, you can also look at the abstract syntax tree and just look at the edit distance of the abstract syntax tree of the different codes. Okay. So what we did is you have human eval there. You have code textbook here. So what we did is we search all the questions in code textbooks that are in code exercises that are close to something from human eval, and then we just remove them entirely and retrain on the subset which does not contain all of this. And let's see what happens. Okay, so this is important and interesting, but again, ultimately irrelevant. So you can have different settings of the sensitivity. How do you consider that something is close? So either 0.95 or 0.9, it doesn't really matter. Now let's look at 0.95. In that case, so human eval is 164 problems. It turns out that 71 of those problems were deemed to be similar to something in code exercises. So we removed these 71 similar, all of the things that were similar to those 71 problems, we removed it. And then we retrained. And now look at this. This is really interesting. On those 71 problems, okay, that were deemed to be similar to something in code exercises and that we removed. Before, the accuracy was 81%. Now the accuracy is 74%. So it went down a little bit. But look at that. On the non-similar one, the accuracy before was 26.9%. Now it's 32%. So this went up, the accuracy on the non-similar problem. And now the beauty is the sum of the two, or the average, is the same number. Okay, you get exactly the same score. And what's even more interesting is that you can look at StarCoder. StarCoder, I don't know on what it was trained, but you can look at the accuracy on the problems that were deemed to be similar, it's 57%. On the problems that were deemed non-similar, it's 29%. Okay, so you see that those problems that were deemed to be similar, they are also easier for StarCoder, even though StarCoder has nothing to do with this whole process. And the reason why I hate this slide is because these 71 problems that are similar, these are just basic questions, that any student will learn. Like, is it because you know bubble sort by heart? Is it a problem that you know it by heart? Does it mean you don't really understand it? Do you have to come up with it without having ever seen it to be able to claim that you understand it? I think it's ridiculous. Like it doesn't make any sense. It's trying to handicap the LLMs for no good reason. So that's why I think, but it's only a problem from a benchmark perspective. But the benchmark are just supposed to test whether the model is good or not. It shouldn't influence the way you try to do the best job to get the most intelligent model. It's like a vicious cycle. The right thing to do is to try to go beyond those benchmarks. Okay, so yeah, I want to stop here and maybe take a last question. Yeah, thanks. Yeah, in the back.
Microphones. Switch it on, I think. Which?
Test.
Oh, there you go. You go.
Thank you. Hallucinations, small models versus large models. Is there a difference? How do you see that evolving?
So no, there is not really a difference. It's a problem for both. Yeah, hallucinations are kind of baked into the way those models are trained. I think there are many ways to try to make progress on them. One of it is to not just take the LLM, but to, again, hook it up with the web, with a web search, and to do RAG, and to have, maybe another LLM that looks over the first one. So I think there are many, many things that we can do to improve hallucination, but just the pure pre-training will not solve it.
Is it worse or same as?
I think so. It's the same story. So in the sense that from Phi 1.5 to Phi 2 to soon Phi 3, we see hallucination keeps going down as we improve the data, as we train for longer, as the model gets slightly bigger. So it's the same story as for the big model. For the big models also, hallucinations keep going down. Whether it will eventually go down to 0 or not, that is a question.
Very good. The next question, maybe.
On the example you show, where the system looked at the diagram of the sphere,
yes,
and you didn't tell it what it was, and then it figured out that. Yeah. Is there a way to open the box and see how it represented and recognized what it was to find the answer?
Yeah. So I worked on trying to open the box before GPT-4. I have this paper. It's called Lego, where we understood some things. I mean, maybe I don't want to give it would take 2-3 minutes to explain. I won't do it. But the short version is, I don't think it's really possible to understand what's going on inside. There's no sparsity, in the model. Like everything is on top of each other. So even like a single concept, there is no reason why, I don't know, the fact that Paris is the capital of France, that this would be stored in a single neuron. From the perspective of the model, it could, distribute it everywhere. And I think everything is distributed everywhere. So it's very, very hard to do interpretability work. But that being said, it's a huge topic and one where academia could try to make progress.
So I have the microphone. Now I'm asking a question. So I wanted to ask you, if I'm understanding everything you spoke about is clever ways, and even Python scripts and even other LLMs that create prompts. The prompts create text through that goes in GPT. Then GPT responds, that creates training. Then you just run model.fit. Like the training algorithm is a commodity. There's no cleverness in the training.
Zero.
And then there is no cleverness whatsoever also in how this thing is decoded. So basically, so I want to ask you, if I had access to GPT-4 where I could see the logics, right? And I could open the box and look at the weights, first of all, did anything you say do anything like that? Or do you see there is interesting work beyond, because everything here is, I think it's a paradigm change. I think it's fascinating. Yeah. But I'm asking, do you find anything in the old ML where we were teaching kids, PyTorch to actually backprop through things and look at, the tensors and do things that we teach, as opposed to teaching them, okay, it's all about how you prompt these new crazy machines to create data sets, and that's where all the cleverness is.
Yeah, so first, I really don't want to give the impression that it's just about prompting. Like I try to explain with tiny stories that there is a seed of creativity came from somewhere else. It came from this vocabulary of 3,000 words and picking 3 at random. You can imagine this part, you can do very, very clever things.
No,
Maybe
prompting is amazing. I mean, there's
Right.
all kinds of prompting.
right.
Yeah.
I guess what I mean is that it's like you still want to anchor it somewhere into real data. You know, for example, like we have generations around healthcare. We're using, you know, PubMed and like actual research papers about medical things to prompt the model. So there is that part. But then to your other question, I mean, yeah, I don't know about the old. I don't want to answer whether the old ML has anything to say about what's going on now. But what I can say is that yes, there are very exciting things that you can do when you open the black box a little bit more. Let me give you one example, again by Ronan with Mark Rasinovich. So this is their paper. It's called "Who is Harry Potter?" And what they did is that they made Llama 2 forget who is Harry Potter. And the way they did that is very, very clever. And you have to have access to the weights, to the logic. So I really recommend everybody to read this. It's really a great example of the kind of innovative new work, which is both has some flavor of the old world, but is also very relevant to the new world.
Thank you. Have time for more?
I don't know.
Seb, wonderful presentation. Love that, the way you explain. You're a very good teacher. I do appreciate that. Someone asked me this question and I honestly didn't have an answer to that. And I want to ask the same questions. And the question is, if everyone is using internet data, everyone has access to books, why everyone cannot take one model and then try to improve that one model? Why we have a race of building model A, B, C, D, and so on?
Right. So, I mean, first, you know, there are the economic incentives that are in the background of all of this. Like, you know, if Meta has a model, you know, Microsoft wants a model, Google wants a model. So there is that part. But then there is also, you can see that in what I'm presenting, I think to make real progress, you cannot just train on unfiltered web. The way you make progress is by being clever, at the very least with the filtering. And also, I think in the synthetic creation, but at the very least in the filtering. And all those different companies, they have different ways to filter the data. So they actually have different training sets under the hood.
Other questions? Sani? Hold on.
I am curious because you guys did a really great job in using the data space of another model, like existing model, and creating synthetic data, then teaching a classifier, like for deduping. Do you think that there is some window of creativity left when one could use the parametric space of another model?
How do you want to use the parametric space of another model?
Like we can use some of the existing model to in a innovative way to retrain our own model, let's say small models or something.
You say reusing the weights in some ways. Yeah, absolutely. So one thing we did for Phi 2, but the problem, okay, we did it for Phi 2. So what we did is Phi 2 was not initialized from random weights. It was actually initialized from Phi 1.5. Now, Phi 1.5 and Phi 2 are not the same size, so you need to do some clever tiling. And we did see a boost. No, it's not in the, no, we did say we did some innovations around scaling. But there is this one sentence. Yeah, every sentence matters. But the truth is I don't fundamentally believe in it. I think if we just train longer from random initialization, we would have gotten, like, it's a way to improve the process a little bit, you know, but it's not fundamental.
Let's thank Seb again.
Thank you.
We have a coffee. We have a coffee break now, and then we'll start back up at 11:30 with Dan Roth.
Yeah, nice job. Great.